All right, here's a video with numbers 5 and 6 from your Unit 8 review. 1,200 kilogram elevator, which can carry a maximum load of 500 kilograms. Oh, you know what? I think on the hard copy of the answer key, I forgot to add this. Oops. Well, that's going to change the answers for some of these, so just going to change the mass. So sorry about that. I'll make a note in the our Google Classroom about that, and I'll fix them on here. So how much power is required to do this? There's two different ways you can do this. Our equation, our mathematical model for power is that it's equal to energy over time, like how much the energy changed over time, or force times velocity. Either one of those will work, and you can do either way here. So let's say you wanted to do it the change in energy. So power is equal to change in energy over time. Well, how much does the energy change for this elevator? Well, in 1 second, if it's going up at 1.5, sorry, that got broken up there, that's weird, 1.5 meters per second, then in 1 second, it goes up by 1.5 meters. I mean, that's what it means to be going up at 1.5 meters per second. So let's see, that means that the change in energy, which is a change in gravitational energy, that's what's happening to the elevator, it's EG. So that's going to be M, which should be 1,700 times 10 m, and then the h is going to be 1.5 meters in 1 second. So this calculation here, this is how much the EG changes in 1 second. And that's going to be, let me just run that through my calculator again to get the right number. That's going to be 25,500 watts. Now, what if you wanted to do it this way? Well, if the elevator is going up at a constant velocity of 1.5 meters per second, then that means that the lifting force and the gravitational force, since it's going at a constant velocity, those would have to be equal. So if we want to do the force times velocity way, power equals force times velocity, the force of lift has to equal force of gravity, and the force of gravity is just 10 times mass. So that would be equal to 10 times the mass times the velocity. And if you look at what's happening there, it's the exact same numbers, comes out to be the same thing, so you still get the same here. For part B, this is a little bit tricky because you have to figure out how much force it's going to take to get it to accelerate with this acceleration. So this problem here, B, definitely has some throwback stuff for things we learned in earlier units. So if it's accelerating, I'm just going to make this little force diagram again. If it's accelerating up, that means there's got to be some unbalanced force in the up direction. It means the up's winning. So this lift force here has to be bigger. And we could write the little unbalanced force equation. Winner minus loser. And unbalanced force is equal to mass times acceleration. Well, here, if it's going to accelerate to this speed in 2 seconds, then we also have to remember that acceleration is equal to change in velocity over change in time. So if it's changing from 0 to 1.5 and it takes 2 seconds, the acceleration is going to be 0.75 meters per second squared. All right, so that means when we come over here, this is unbalanced force equals mass times acceleration. So mass is 1,700 times 0.75 that I found here, and that's equal to the lift force minus force of gravity is still 10 times the mass. So the lift force is equal to, if you do all the math here, let's see what we get. You get about 18,000. I'm going to call that 18,300. It'd be too many sig figs to write down what my calculator's saying there. Newtons. Okay, so if that's the force, then now we can finally find power is equal to force times velocity. Well, the velocity is changing, but it's gonna, the motor has to do the whole thing. So as the velocity increases, the power is going to become more and more, it's going to require more power. So that means we should take the biggest velocity, in other words, the 1.5. It's going to start from 0 and it's going to creep up to 1.5, but the power required is going to include the biggest it's ever going to get. So that's 18,300 times 1.5, and that is about 27,400 watts. And you can see that that's bigger. That's what we would expect that to be, a little bit bigger than how much power was required to just move the elevator up at a constant velocity. So there's that. A lot of good stuff in that one, but that's pretty tricky. I would go back and you can try to repeat what's necessary to do that. Practice doing that again. All right, last question, number 6. A postal worker spends 8 hours a day, 5 days a week, lifting 15 kilogram boxes from the ground onto a shelf that's 1.5 meters high. So if the worker lifts 15 boxes every minute, what's that power output? Power output is energy over time. So I could just figure out what it is for one box and then divide by time, and that would be the power output. You could do it for more boxes, it doesn't matter. But the easiest thing, I think, would be to figure out what is the change in energy for one box. So delta E, the thing that's changing about the box is its gravitational potential energy, putting it up on the shelf. So that's equal to the mass, 10 times the mass of one box times the change in height for one box. And that's 225 joules. That's the change in energy. So how long does it take the worker to do that? Well, if they're doing 15, where did it go? 15 boxes in a minute, then how much, then that would be one box. How long would that take? Well, 15 boxes every 60 seconds, so that's one box is going to take 4 seconds. And that means that our power is we're doing this much energy every 4 seconds, because this is one box, that's the time for one box, and put that in your calculator, that's about 56 watts. And since we're going to be talking about kilowatt hours in the next one, in the next part, I'm going to go ahead and just put off to the side here that 56 watts is the same as 0.056 kilowatts, just like changing meters to kilometers. And we're going to need that in the next problem. All right, so if the electric company is paying 10 cents for every kilowatt hour, then how long would the worker have to work to make 10 bucks? Let's see. Now, this is just paying for pure power here, so this is not actually what people get paid for, and you might be surprised to see what the answer to this is. So anyway, let's see. So if we need to know, we're talking about 10 bucks here, and this is 10 cents for every 1 kilowatt hour. So for $10, that's multiplying this by 100, right? 100 dimes is 10 bucks. So multiplying that by 100, that means $10 is going to get you 100 kilowatt hours, right? So that's what we're talking about. So we need to know how long it's going to take our worker working at this speed to get 100 kilowatt hours. Well, 100 kilowatt hours is 100 kilowatts times an hour. And we need to know if our worker is doing 0.056 kilowatts, and we're trying to figure out how long it's going to take them. And this time, since this is hours, that time's going to come out in hours. So if we divide this over here, we're going to get about 1,800 hours. Oh, that's weird. I don't know how I did that. I made a little circle. I have no idea how I did that. I'm going to erase it now. Nope. Well, maybe I won't erase it. So there. 1,800 hours, and that is a long time, but people don't actually get paid in this way. People don't get paid the same amount that electrical power is equivalent to. And 1,800 hours, if you're working 8 hours a day, just to give you an idea here, 1,800 hours divided by 8 is 225 days. And if you're working 5 days a week and you get a couple weeks off for vacation, that's almost your whole work year right there. I mean, heck, we only go to school for we used to only go to school for 180 days a year. Now I think it's gonna be a little less than that this year. So anyway, there you go. There's your solutions for the Unit 8 review. Hope you're doing okay.